We're back at AP Review. We are doing 2016 BC free response number 6. The function f has a Taylor series about x equals 1 that converges to f of x for all x in the interval of convergence. It is known that f of 1 is 1 and f prime of 1 is negative 1/2. And that the nth derivative of f at x equals 1 is given by the nth derivative of f at 1 is negative 1 to the n times the quantity n minus 1 factorial, all divided by a 2 to the n for n values greater than or equal to 2. Part A, write the first 4 non-zero terms and the general term of the Taylor polynomial about 1. Okay, so for part A, remember the way a Taylor polynomial works, and I'm using 1 instead of a here, is that the first term is f of 1. We're used to seeing that as an f of a. The next term is f prime of 1 over a 1 factorial, but we never bother to write it, x minus the a, but in this case that's a 1, to the first, plus the next term is f double prime of 1 over a 2 factorial times an x minus 1 to the second. The next term is going to be an f triple prime of 1 over a 3 factorial times an x minus 1 to the third, right? And when we get to the nth term, it's going to be the nth derivative at 1 over an n factorial times an x minus 1 to the n, right? That's what we're looking for. So if we look at this stuff, we know some of these things, right? We know f of, I'm going to inch a little this way. We know f of 1, we know f prime of 1, and then we're going to need to use the formula that we were given to find these two values, right? So wherever you want, like somewhere on your paper, you would need to plug in n is 2 to find the second derivative. So I'm going to squeeze this up here. If I were to plug in n is 2 to find the second derivative here, I'd get f double prime of 1 equals a positive 1 times a 1 factorial all over a 2 to the first. So I end up getting that f double prime of 1 is a 1/2. Okay, so now I know that guy. If I want f triple prime of 1, I'm plugging in n is 3, right? So that would be a negative 1, because it'd be negative 1 to the third, which comes out negative. I'd get a 2 factorial, which is just a 2, and it would be over a 2 to the third, which is an 8. Oh, I'm sorry, it was a 2 to the second up here. My bad, that was a 4th. Sometimes my brain does stupid thing. So I get a negative 1/4. So I got a 1/4 for f double prime of 1, and I got a negative 1/4 for f triple prime of 1. So now I know all of these things, and it's just my job to write out this ridiculous mess. So I'm going to get a 1 minus a 1/2 times the quantity x minus 1, plus a 1/4 over a 2, which is a 1/8 x minus 1 quantity squared, right? A negative 1/4 over a 6 would be a negative 1/24 x minus 1 to the third. Now that's my first 4 non-zero terms, plus dot dot dot. Now at this point, you might be hoping to see a pattern of the coefficients that make it so that you can just anticipate what this one's going to be, and you don't here. So what's going to happen is I'm going to have to plug in this ugly thing here and simplify it over that n factorial. So what's going to happen when I do that is I'm going to have an n minus 1 factorial. So I'm going to write this down here actually, and then I'll put the polished final answer up here. This is a negative 1 to the n minus 1 factorial over this 2 to the n, and then also on the bottom of this fraction will be this n factorial times this x minus 1 to the n. The only things that cancel here are these factorials, and everybody but the n on the bottom is going to cancel from that, because n factorial means n times n minus 1 times everything below n minus 1. So this whole top factorial cancels, and I just get an n on the bottom. So I end up getting that this is a negative 1 to the n times this x minus 1 to the n over an n times a 2 to the n. And that's my long answer for part A, right? So let's go on to part B. So when we get to part B does me a solid and says, the Taylor series has a radius of convergence of 2, which means you don't have to do the ratio test. So thank you, AP, for not making me do the ratio test. They then say, find the interval of convergence and show the work that leads to your answer. So since they did you the solid of giving you the radius, all you have to do, since you have the radius, and I'm going to take the risk of erasing this, knowing that I might aggressively regret it, I'm going to need this a sub nth term. So hopefully I don't forget it when I go to recopy it. So since you know in part B, that my bad, too far over, that the radius of convergence is 2, and you know that the center is at x equals 1 because that was given at the start of the problem, the situation you're looking at is, here's 1, you could be 2 units away at 3, or you could be 2 units away at negative 1. Those are your two options. So what you have to do is you have to take this nth term, which we know is negative 1 to the n, on the bottom there's an n times a 2 to the n, and the top has just the x to the n, the x minus 1 to the n. Yeah, that seems right. Okay. So I'm going to try the two different x values and see if I get a convergent or divergent series at the endpoints. So I'm going to test x is -1. When I plug in x is -1, I end up getting that my a sub nth term is a -1 to the n, a -2 to the n, right, -1 and -1, over an n, times a 2 to the n. Right. So what I want to point out here is I can split this -2 into two things. I can treat this -2 as a -1 to the n times a 2 to the n. And the reason that's useful is there's already a 2 to the n on the bottom. So these guys end up canceling. And what I end up with is a -1 to the 2n on top of an n. Well, 2n is an even number, so I get a 1 over an n. This is the harmonic series. Right? So if your a sub nth term is 1 over n, it's the harmonic series, and the harmonic series diverges. Now, what usually happens in a problem like this is that one endpoint yields the regular harmonic series, like this one did, right? And the other endpoint yields the alternating harmonic series, which totally converges. So we can't know that's going to happen, but that seems, you'll see that enough in problems that it's pretty common. So if I plug in x is 3, my a sub nth term is -1 to the n, 2 to the n, over an n times a 2 to the n. Well, those 2 to the n's cancel, and I get a -1 to the n over n. Oh, look, it's the alternating harmonic series, right? So it's the alternating harmonic series, which converges. So my interval of convergence, right, my answer is going to be that I can't include the -1, but I can include the 3. Or if you write it the way I prefer, because I'm a huge fan of parenthetical notation, parentheses -1, comma 3 with a bracket, right? Just make sure your brackets look really brackety and your parentheses look definitely like parentheses, right? You don't want to make any mistake there. Cool. Part C. The Taylor series for f about x equals 1 can be used to represent f of 0.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. I think I just said f of 0.2 when I read it the first time. I apologize. All right, so part C. All right, so we know from our original part A, right, that f of x can be approximated by using, we had a 1 minus a 1/2, x minus 1 plus a 1/8, x minus 1 squared. They asked you to use the first, first 3 non-zero terms. 1, 2, 3, that's non-zero. Okay, so we know f could be used to approximated by these terms, right? That was our answer to part A, but instead of giving the entire thing, we only gave the first 3. One way you sometimes see this is like a p sub 2 of x, right? Because it's up to the second degree. Anyway, so f of 1.2 is approximately a 1 minus a 1/2 times, if you do 1.2 minus 1, you get 0.2, right? Plus a 1/8, and again, if you do 1.2 minus 1, you get 0.2 squared, right? Now, this is number 6, so it is a non-calculator section, so you are going to have to math a little, and, you know, life's hard, wear a helmet. If it helps you, I find it helpful, I think, to treat this as 1/5. I think that's a lot easier, because then you're going to have a 1/2 times a 1/5, right? Which is a 1/10, right? And that's not awful, right? We're pretty decent with 1/10. And by the same token, if this is a 1/5 squared is a 1 over 25. And you can do 25 times 8, hopefully without like completely breaking your spirits. 25 times 4 would be 100. So 25 times 8 is 200. So this is going to be plus a 1 over 200, right? And there's a couple ways you can go here. I mean, honestly, common denominators aren't awful, but you could just as easily turn this into decimals. Because the other way to think about this is this guy is a 1/2 times a 1 over 100, right? So if you want to convert this to decimals, this is a 1 minus a 0.1, right, plus a 0.005. So, because that would be half of a 100th, right? A 100th would be here, so half of it would be 0.5. So, and if you do that and you combine your like terms, you get that this is approximately a 0.905, right? So that's your f of 1.2. Part D, show that the approximation found in part C is within 0.001 of the exact value. So this is asking you, oh, sorry, this was part C. This was asking you to do error, right? So the trick with error, when we talk about D, this is an alternating series, so they'll sometimes say use alternating series error, but here's the short version. If you want to find the error, which means the difference between this approximation, right, like this value that we got, so if you want to find the error, which would essentially be, I would suggest that you call this something like p sub 2 of x, right? So your error would be the actual value, f of 1.2 minus p sub 2 of 1.2, right? This goes up to this term. You want to say that that is less than or equal to the next term maxed out, right? So next term maxed out on, and the window you want to max it out on, oh, I'm sorry, I made that a 5 and it's a 2, on the window from 1 to 1.2, because one of these is the center, which in this case was 1, and one of them is the value you're given. So if you look at the next term, if you go back to part A for a sec, right? So if you go back to part A, the next term in your expression was a negative 1/24 x minus 1 to the third, I'm pretty sure. So we get that, and we say, okay, cool, I want to max that out. Well, the thing that's going to make it the biggest is if I make this a 1.2, right? If I make this a 1.2, because if I make it a 1, it's a 0. So I'm going to get this the absolute value of a negative 1/24, although the negative's basically irrelevant, and then a 0.2, right? So I'm going to plug in this 0.2, which is the same as a 1/5 cubed, right? So I want to show that that quantity is smaller than 0.001, right? So if I clean this up a little bit, right, I don't need the negative anymore, so let's just do a little bit of math to clean this guy up here, because again, it's a non-calculator section. If you were really in a pinch, you could be like, yo, that's smaller than this, cool, I call it a day. Like if you're really panicked and you're like, hey, I'm out of time and I quit, then just accept that this is what they're asking you to do. Sorry, there was a third on that. This is what they're asking you to do, and they want you to show the chain that if this is smaller than this, it's smaller than this. But if you're going to do the math for it, you've got a 24 times a 125 on the bottom. Now, just a little mental math, because this makes life a lot easier. It's easier to multiply even numbers for most people, so I'm going to make this a 12 times, and then I'm going to double this guy and make him a 250. Right? And then I'm going to make my life even easier. I'm going to take this 12 and I'm going to make this a 4 times a 250 because that's 1,000. So I realize that, oh, hey, this is actually a 1 over 3,000, right? Well, this guy is a 1 over 1,000. Bigger denominator, smaller fraction. So 1 over 3,000, which is what this thing is definitely smaller than 1 over 1,000, which is what this thing is. So sure enough, my error is smaller than the number they gave me, right? These error problems always come down to a chain, right? This is the error they want. They want you to say it's smaller than whatever happens when you max out the next term, and then that number that you get should be physically smaller than whatever number they made up to use for the error.